All right, so this is section 3.5, chapter 3, applications of differentiation. Section 3.5 covers summary of curve sketching. Okay, how do we sketch curves and how do information about derivatives and second derivatives help? Okay, let's try guidelines. So, first, the following checklist is intended as a guide to sketching a curve y equals fx by hand. Not every item is relevant to every function. Okay, this is important to note. For instance, a given curve might not have an asymptote or possess symmetry, but the guidelines provide all the information you need to make a sketch that displays the most important aspects of the function. Okay, so you have a long checklist coming up. So I have a file here. Let's write down the important points. Okay, A, it is the domain. Very first thing we have to check is the domain. The domain of f is the set of values of x for which fx is defined. Okay, so A is the domain. What is the domain? It is the set of points, set of values of x for which fx is defined. Okay, this is an important point. So first figure out domain for the given function. Next, intercepts. You need both the x and y intercepts. Y-intercept is where x is 0 and x-intercept is where y is 0. Okay, so B is intercepts. All right, how do we find intercepts? To find y-intercept, you set x to 0 and solve for y. To find x-intercept, set y to 0 and solve for x. Okay? C. Here we look for symmetry. Okay? Whether your graph is symmetric one way or which way is it symmetric. All right, let's understand this. If f of negative x is same as fx, such a function is called even function. Okay, when we change the sign of x and yet get the same value. Okay, in such cases the curve is symmetric about the y-axis. Okay, so first point is even function. What is an even function? F of negative x is same as f of x. The curve is symmetric about the y-axis. All right. So this I hope is clear. Look, if you think about it, what happened here? If you think about it, let's look at a graph. Say if I have a graph of a function such that the value for a positive x, okay, is the same as the value for its negative x. That is, if for this on the right hand side, my height is here, then if my function is even, then on the negative side, it must occupy the same height. So for example, something like y equals x squared. Okay, if I take positive x value or negative x value, I get the same height. Okay, so such a function is an even function. So notice how it is symmetric about the y-axis. Okay, next. This is about symmetry for an even function. What happens? Some more examples, okay? Y equals x squared, x to the fourth, absolute value x, cosine x, okay? These are all even functions, okay? Now, odd function is when you change sign of x, you change the value of fx, okay? So, in other words, okay, I'm looking at odd function. When I change sign of x, the negative comes out, okay? Here, the curve is symmetric about origin, okay? What does that mean? You see, for example, fx equals x to the power 3, okay? This is an example of an odd function because, say, f at negative 3 is what? Negative, I shouldn't take too many 3's. Say f of negative 5. It is negative 5 to the power 3, which is negative times negative times negative, negative 125. All right. On the other hand, if I look at f of positive 5, it is 5 to the power 3, that is 125. In other words, notice when I put a negative inside, it actually came out, correct? So what happens in this case to the graph? Well, let's draw. If you remember the graph of x cubed, on the positive side it looks like this, on the negative side it looks like this. In other words, you have to reflect it once and once again, or reflect it this way and once again. So in other words, you're reflecting twice about the axis, okay? Or another way of understanding this is there is a rotation. This curve gets rotated by 180 degrees, okay? So that's what is symmetry about the origin, okay? So f is an odd function. The curve is symmetric about the origin, okay? So we can obtain the complete curve if we know how it looks like for the right hand side, that is x greater or equal to 0. You take your curve and rotate it 180 degrees, okay? Another way of thinking about it, reflect, reflect once more, or reflect, reflect once more, okay? So all these functions, y equals x, x cubed, x to the 5, sine x, these are all examples of odd functions symmetric about the origin, okay? Next, periodic functions. So if you have a positive constant p such that f of x plus p is fx for all your numbers in the domain, then f is called a periodic function. The smallest such number p is called the period, okay? For instance, you have sine x. Sine x has period of 2 pi. After every 2 pi, it repeats, whereas tan x has period pi, okay? If you know what the graph looks like at an interval p, then you can use translation, okay? So I hope this is clear. So the next item on symmetry is periodic functions, okay? So you want f of x plus p equals f of x. So when you add p, okay, you get the same quantity back. So different functions will have different periods. For instance, if you look at sine, if you look at sine, okay, because this is one cycle. So you start at 0. Here at pi, you hit 0 once again. And at 2 pi, you hit 0 once again. This is your sine curve. If I wish to extend this as to the right some more or to the left some more, what do? I take this picture and repeat. That's the purpose of period. And that is all you need to know is how the graph looks like at that certain period. After that, you just have to repeat. Okay? Hopefully you'll repeat better than I do. But anyhow, do you understand that this is a repetition of this? Okay, and so on. This is sine. Sine has period 2 pi, whereas tan has period of pi. Okay. So tan goes from negative pi over 2 to positive pi over 2. Okay, and these are the two asymptotes tan has. So it looks something like this between the two. Tan is an odd function, by the way. Okay, so now you know the graph of tan between these two numbers, negative pi by 2 and pi by 2. So how do I extend the graph? So how do I know what the graph does after this? Well, from pi over 2 to 3 pi over 2, I have to simply repeat the picture. Okay, that's the advantage of knowing period for a function. If a function is periodic, then all you do is repeat your picture, no more calculations. So take this and cut and paste again. All right, so this was 0, so this is pi. Okay, that's the purpose of periodic functions. Next item, asymptotes. You want horizontal asymptotes, or you're looking for vertical asymptotes, or you're looking for slant asymptotes. Okay,